Okay, this is my second attempt. I think I just made an entire video and didn't realize it didn't record my audio. So this will be try 2. So we are going to look at acid-base titration curves. All right, so the idea is we have our burette. So I'll say this is my burette. I'm going to have my flask down here, and in my flask I'm going to have my stir bar, and this will be sitting on my stir plate. And then I'm usually going to have my base in my burette, and I'm going to have my acid down in my flask. And now I'm going to put in here a pH meter. So I'm going to monitor the pH while I'm adding base. So that means to start out with, I'm going to have an acidic pH. I'm going to be adding base. I'd add a little base, take the pH, little base, mix it, read the pH, add a little more base, mix it, take the pH. And what I'm going to get out of that is a graph. So if we'd been doing this for our lab, we would have had a pH sensor in here, and this titration would have taken quite a long time because we would add a milliliter of base, read the pH, add another milliliter of base, take the pH, so we wouldn't just titrate it all the way through. The other difference is that when we reach the equivalence point and our indicator changed color, we would keep going beyond that until I had added several more milliliters of base. So if I had an acid, I would start down here with a low pH since it's a strong acid. As I added base, that pH would increase, and all of a sudden it'd reach a peak, and then it'd kind of level off again. Now this tall region, halfway on this tall region, is what's called that equivalence point. And that equivalence point is when I have the same number of equivalents of acid as the equivalents of the base. And when I'm talking about those equivalents, that's what we did in the acid-base lab 2, where we looked at normality and equivalence. So at the equivalence point, the equivalence of the acid is equal to the equivalence of the base. And typically, when I am looking at these, and on your lab we'll be looking at 4 different points. We will be looking at the pH before I add any base. I'd be looking at the pH halfway to that equivalence point. So this is about halfway to that equivalence point. Down here, this would be my volume of the base that I'm adding. This would be my pH. So if this is the amount of volume at the equivalence point, halfway would be here, and I could read that pH. I would read the pH at my equivalence point, and then I would go beyond the equivalence point and read the pH up here. So before any base was added, halfway to the equivalence point, at the equivalence point, and then beyond the equivalence point. Now this is what it's going to look like if I have a strong acid in my flask and I'm titrating with a strong base. This curve looks a little bit different if I have a weak acid and I'm titrating with a strong base. So I still have the same kind of graph. I'm still going to start with a low pH because I have acid, but now what's going to happen is it's going to rise, but this region that's vertical is going to be narrower, so it's not going to be as tall. And this region is going to be kind of a buffered region. Now if I were to reverse this and put in a strong base in my flask that I'm titrating and then add a weak acid, what would happen at that point is I would start out with a base. So I'd have a high pH, and then my equivalence point would be there. So it'd pretty much be a mirror image of this one. Instead of starting with a low pH and going to high, I'd start with a high pH and go to a low because I had base to start with and I'm adding acid. Now, if I were to make both of them weak, and you're not going to have one in your lab like this, but if I had a weak acid and a weak base, then it's going to be buffered at the beginning, very small vertical region, and buffered at the end. My equivalence point is still halfway on that vertical region. It's just that that vertical region isn't going to be very tall. Like in this case, I had a big, tall vertical region. So if they're both strong, I have a big, tall vertical region. If one's weak, that vertical region narrows, and if they're both weak, really narrow vertical region. But again, the equivalence point is still in the middle of that vertical region. Okay, now we want to talk about indicators. So if I have, we're going to go back and look at a strong acid with a strong base because that's the one where it's easiest to see that equivalence point. So if I look at several different indicators, those indicators are going to be different colors. So let's say that I'm going to choose an indicator like phenolphthalein that turns pink. And phenolphthalein usually turns at like a pH of 8 to 10. So that means my indicator would change color about here. Then let's say I would choose a different indicator and maybe it's going to be like bromethymol blue, and let's say it changes color here. And then I have a different indicator, let's say it's like methyl orange, and methyl orange has a range that is low down here. So depending on what indicator I choose, it's going to change at a different pH range. And it's very important for me to choose an indicator that changes color at my equivalence point. So for this particular titration where I have these three indicators, the blue one would be the best indicator for me to use because it's the one that's changing color at my equivalence point. I want the endpoint when the indicator changes color to be the same as the equivalence point. So it does no good for my indicator to change a color up here because then I've missed my equivalence point. So I want to choose an indicator that changes color at the equivalence point. And the lab that you are going to be doing the simulation at the end of the week, it's going to auto titrate for you. So if you select auto titration, it runs it through and it shows you what the curve is going to look like. And then you're going to be reading those regions, you know, before you added anything, halfway to the equivalence point, at the equivalence point, and beyond the equivalence point. And then another part in that lab, I give you a table that has indicators in it and when they change color. And I ask you to choose a suitable indicator for each one of the titrations that you do. So you're going to want to make sure that you choose that indicator that changes color at a pH that is overlapping your equivalence point. Okay, so that's kind of the background of what these curves look like and how you choose the right indicator. Now we're going to go and look at how do we solve a problem. So I'll pick out one, and I think this one we're going to do is a strong acid with a strong base. All right, so we have, in this case, 20 milliliters of a 0.200 molar HBr, and I'm going to titrate that with a 0.200 molar NaOH solution. So I have a strong acid and a strong base. And they want me to calculate the pH when I've added 15 milliliters of base. They want me to calculate it when I've added 20 milliliters of base. They want me to do it when I've reached 35 milliliters of base. So in this case, we're going to be doing it not at the very beginning, but partway to the equivalence point, at the equivalence point, and beyond the equivalence point. Okay, if they wanted me to find it before I added any base, that means this would be the molarity of my HBr. So that means my H plus molarity would be 0.2. And that means my pH would be negative log of that. So my pH would be 0.7, looks like I get 3.699 molar. So that would be the pH before I added any base. And since it's a strong base, you can see the pH, well, no label on a pH, sorry guys. My pH would be very, very low. All right, so we're going to go on and we're going to do these other three where I'm going to add some base to each part. All right, so I have HBr, and I'm adding to that NaOH, and I'm going to make water and a salt, which is going to be NaBr. So for all of your acid-base titrations, it's always acid and a base makes water and a salt. And if you have added any of the base to this, this is going to require an ice chart. Now, before I added any base, I didn't need an ice chart because I had a strong acid and I knew all of it ionized. Now, I need to use moles in here just like I did for buffers. So I need to go back and calculate my moles. So for my HBr, I have 0.2 molar. That's moles over liters. So I have 0.004 moles of HBr. Now that's going to stay the same the entire titration because this isn't changing up here. Now for my base, I have 0.2 molar. And for part A, I'm using 0.015 liters. So I have 0.003 moles of the NaOH. Okay, so I'm going to fill those in. I have 0.004 of my HBr and 0.003 of my NaOH. I don't care about water, and I don't have any salt. Now, just like I did for buffers, I want to pick whichever one of these is smaller, which is the NaOH. So minus 0.003 minus 0.003 plus 0.003. Now, this is not a buffer because this is a strong acid, and I can't use a strong acid or base in a buffer. So I have a neutral salt, which I don't care about right now because I have excess strong acid. So that means that my molarity is my moles, 0.001, and I added 15 milliliters of base and 20 milliliters of acid. So here's my 20 of my acid, and I added 15 of the base, so that's 35 milliliters. Point 02857. This is the molarity of my HBr. So that means my H plus molarity, since all of it would ionize in a strong acid, the molarity is 0.02857. So my pH is negative log of that concentration. And I had 3 sig figs, so I get 3 decimal places. So pretty low pH, but you can see that before I add in any, I had 0.699, very, very acidic. I've added some base now, and my pH has come up a little bit. Okay, for the next part, I'm going to be adding 20 milliliters. So I'm going to use the same exact setup. In fact, I'm just going to go through and erase these parts. All right, and now the molarity of my NaOH is, I need a new way to find this. I'll put it over here. So 0.2 is the molarity of my NaOH. And then I have moles, and now I'm adding 20 milliliters, so 0.02. So that means I have 0.004 now of the NaOH. These are the same. So 0.004. I have no acid left, no base left. All I have left is this salt, and this is a neutral salt. So at my equivalence point, if I have a strong acid and strong base, the pH is 7. So didn't really take a whole lot of effort for me to find that one. Okay, now we're going to add more base. And notice I've been using the same exact equation the whole entire time. Okay, so now I'm adding 35. So this is going to be 0.035. So this is 0.007. So the 0.004 is smaller now. All right, I have a neutral salt, but I don't care about that right now because I have excess strong base. And since I have 0.003 moles, and I had 20 of the acid, and I added 35 of the base, that means I have a total of 55 milliliters. Okay, so that's the molarity of my NaOH, and since that is a strong base, that means that my OH molarity is 0.0545. So I could find my POH by doing negative log. So 1.263. And then I could find my pH by taking 14 minus that number. And I would get 12.737. So before I added any, I had a pH of 0.699. Then after I added some, my pH went up. I think it was like 1 something. And then now I had a pH of 7 at the equivalence point. And finally, I ended up with a pH of 12 because I have excess strong base. So those 4 points that I went through, which were before I added any base, so before any base, then I had added some base. Then I was added at the equivalence point, and then I was beyond the equivalence point. And each time, here I only had strong acid, here I had excess strong acid, Here I had a neutral salt, and here I had a strong base. So all those 4 regions, if you look at the acid-base titration curves reference sheet that I have posted on Blackboard, it's going to walk you through for your lab, and I picked out an example that would be like the lab calculations. It's going to tell you exactly, before you have any, what you have, which was, it had strong acid, and how to find the pH. Same thing for each one of those 4 points. So that reference sheet is going to be very helpful as you do the lab. Okay, so this was a strong acid, strong base. We're going to quit for this video. Our next video, we'll do an example where one of them is weak.